So today we are going to discuss about inferential statistics. So inferential statistics is actually a third section video. So we are going to briefly discuss about inferential statistics. So first we'll discuss some definitions, and second basic approach to computing probabilities, or some how to calculate the simple probabilities. And third, relationship among the events. So in this case, maybe we will explain by using Venn diagram. So then conditional probability. So conditional probability laws. So in this case, we will briefly discuss about conditional probability applications, and also we will discuss that Bayes law, Bayes theorem, or Bayes law, and also finally we will use the counting principle uh, uh, using probability calculations. Right, so first inferential statistics. So what's the inferential statistics? So it involves drawing conclusion. So drawing conclusion about a population based on the information from a sample. The population. It involves gathering data on a sample of population and also involve analyzing this data in order to make inference about the entire population. Alright, so this is the simple example. So in October 2002, ABC News poll found that 73% of Americans favor a law that would require every gun sold in the United States to be test fired first. So law enforcement would have its ballistic fingerprint in case it is ever used in the crime. So this is just a simple example. Second example, a Starbucks manager examined the amount of brewed coffee sold in the last 5 weeks in order to guess the demand for this week. So in this case, usually population parameters are unknown. So but in this case, maybe in inferential statistic mean just we will use the select the sample and also calculate the probabilities, and also finally we will make conclusion for population. So in making the inference about unknown population parameters based on the information from sample of the population, understanding of likelihood or probability is essential. So later we will briefly discuss about how to calculate the probabilities. So probabilities or chance are computed relative to the idealistic or perfect world point of view. So to understand the probabilities and hence the population distribution, the concept listed in next few slides are introduced. So usually our probability calculations, so for population, so suppose if we provide some probability values for suppose particularly one of the event, so actually the probability for whole population, so not in the sample, but maybe some of the situation we will calculate that probability based on the sample information. Okay. Alright, so first we are going to discuss some definitions. So first definition, experiment. So conducting an activity in generating the data. It could be just gathering information or performing an experiment. For example, toss a fair coin 3 times and observe the sequence of head and tails. So 3 times tossing a coin. So maybe 3 times tossing a coin mean maybe all 3 times we can get maybe head, or we can get all 3 times tail, or first 2 times tail, third time head, or first time tail, second time head, third time tail. Okay, so we can try several ways, several outcomes in this case, in this example. So this is we call that as experiment. This is one of the experiment. Next example is record the ages of randomly selected group of graduate from 4-year college. So in this case, this is age. This is one of the experiment. So record the age mean maybe that age possible, maybe some of the numerical values. Alright, so next important definition, sample space. So this is very important definition in probability. So sample space is also called outcome space, set of all possible outcomes of an experiment. So if we write down all possible outcomes in set format, we call that is sample space. For example, for the experiment at tossing a coin 3 times. So 3 times tossing a coin, so we can write 8 possible outcomes. So that means first time head, second time head, third time head. Or first time tail. So okay, sorry. First time tail, second time tail, third time tail. Or first time head, second time head, third time head. First time tail, second time tail, third time head. First time tail, second time head, third time tail. So similarly, we can write this all possible outcome. So this is we call sample space. So usually we denote as sample space is capital S. So maybe some of those textbooks use that notation, maybe omega. So that is also maybe sample space notation. But in this presentations, I am going to use that notation as big as sample space. Alright, so this is another example for the experiment of recording the ages of 4-year college graduate. The sample space is the set of all real numbers between 10 and 80. So in this case, suppose if you write down the sample space, and also in this case they given assuming that there is no non 4 years college graduate because younger than 10 and older than 80. So that means in this case maybe sample space we can write 11, 12, 13, 14 up to 79. Okay, so this is another example. Next definition, event. Any subset or part of sample space we call that is event. So we can divide it that is event is simple event and compound event. So simple event means each individual element of a sample space we call it simple event. Compound event means any event including 2 or more simple event. So that is we called compound event. Next, probability. So maybe probability is this definition, maybe one word definition, this chance of occurrence. That is probability. Alright, so in this case, this is a notation of chance or likelihood is known as probability. The probability values are always between 0 and 1, also inclusive. So that means maybe possible 0 or possible 1. The probability of sample space is 1 and the probability of unlikely or improbable event is 0. For example, what's the probability of getting 7 in tossing die? So in this case, our tossing die case, only possible events may be 1, 2, 3 up to 6. 7 is not possible. So that's the division that probability should be 0. Okay, or otherwise another example maybe probability of getting integer in throwing dice. So that's the division, that's probability should be equal 1 because maybe your outcomes may be 1 or 2 or 3 or 4 or 5 or 6. So those are all numbers integer. Okay, so this is very important. Maybe some of the situations, suppose if you calculate the probability, your probability value, you get some values, maybe negative values or maybe greater than 1 value. So that situation you think about you did some mistake for your probability calculation. So this probability satisfy any situation or any example, any data. So this is actually theoretically we can prove that probability less than 1 and greater than 0 or equal to 0 or equal to 1. Okay. Right, so next we are going to discuss about some basic approaches to computing probability. So first approach one, subjective probability. So the probability of event A is estimated by using an individual personal judgment of the relevant circumstance. For example, James thinks the probability that chamber walls beat rocket this weekend is 70% chance. So this is actually one of the particular person judgment. So this is first approach. So maybe I think maybe 100 years back these people used this approach for that probability calculation. But nowadays we have some standard method for that probability calculation. So this is approach 1. So relative frequency approximation is conduct or observe the procedure in times, and the number of times event A actually occurred is S. So it's time that event occurred, and also we conduct or observe that procedures is repeated n times. So based on this actual result, probability of A is approximately follows probability of A approximately S divided by n. So nowadays we will use this expansion of this result, this approach, this relative frequency approximation approach. So we developed some standard method for that probability calculation. Alright. So for example, this is example for relative frequency probability calculation. In 2009, there were 10.8 million vehicle accidents in the United States. 33,800 people involved in the accident died within 30 days. So based on the data from the 2012 statistical abstract, the probability of the accident death rate in 2009 can be approximated as this one. This is just approximate probability calculation for just application of relative frequency probability calculation. Okay. Alright, so third approach, the classical approach to probability. So nowadays we use this approach. This probability requires pre-assumed chance of the outcomes. So assume that given procedure has n different simple events, and that each of the simple event has an equal chance of occurring. So if event A can occur in of these n ways, then we can write probability of A is equal. So this is the notation, probability of A is equal S divided by n. So this is in this case that n different simple events. So that means number of total outcomes or number of total element in sample space, that is n. This number of element in particular event S. So this is the probability. Okay. So maybe most of the situation we use this formula for our probability calculation. So this is a simple example. In spring 2011, Minnesota State University Mankato had enrolled 719 international students based on the population statistic from MSU International Students and Scholar Service. The total enrollment was about 15,000. The probability that randomly selected MSU student is an international student can be calculated. Just directly apply that probability equation. So 719 divided by 1500. So that should be equal 0.0048. Okay. Alright, so this is another example. So on the first date, Haley asked Mike to guess the month of her birth, not including the year and date. So what's the probability that Mike will guess correctly? So in this case, that probability calculation, so here they mention this month of her birth. So in this case, actually the probability, this total possible outcomes 12. We have total 12 months. So this particular person asked Mike to guess the month. So this birth month is maybe January or February or March up to December. So this is one of the particular month. So that means probability 1/12. Okay. Alright, so next section, relationship among the events. So relationship among the events, this section we are going to discuss this relationship among the event based on some Venn diagrams. So already everybody familiar that Venn diagrams. So let's see. So first we are going to discuss about subset or sub-event. So subset or sub-event. So a subset is portion of the set. So actually the subset is the portion of the set. For example, A is subset of B. So usually we written as A subset of B. So this is the notation. If and only if every member of A is a member of B, which means that occurrence of A will lead to the occurrence of B. So A is subset of B. So in this case, this is bigger set. A is subset of B. So, and also, you know, this A and B are one of the events in sample space. So we can write this. This is that Venn diagram explanation. So this is that event A. This is that event B. So in this case, this is A subset of B. So if you consider any element belongs to A, if and only if that element also belongs to B. So that is subset or sub-event. Alright, so this simple example, so we consider this example 3.3, so that means just we consider 3 times tossing a coin. So in our sample space contain 8 elements. If an event A is defined as one head in 3 tosses, so exactly one head. So that means maybe if you write out that event space, so this event A, this event space only exactly one head, so maybe possible GGH or GHT or HTT. And another event B is defined there at least one head. So at least one head mean maybe exactly one head or two head or all heads. Okay, so if you write out that event space in B, there's that event space. So in this case, this obviously we know these 3 events belongs to this event. So this is A is obviously a part of B. So A is subset of B. Okay. So this is a simple example. So next, complementary event. So complement is the opposite event or event which does not include the elements of the event of interest but include the rest of the elements of the sample space. So let us consider A bar is the complement event A. So usually we denote the standard notation A bar is the complement event of A, or some of the textbooks use this different notation, maybe A complement A prefix C. That's also maybe some of the textbooks use that notation. So for example, if you know the probability of rain is 20% chance or 0.2, the probability of complement, that means not rain, is 80% chance or 0.8, so that means 1 minus 0.2. Okay, so this is a simple example. So this complementary event, so this is maybe we can write down that complementary probabilities. Probability of a complement should be equal 1 minus probability of A. Alright, so this is a simple example. This is event A. So this is event A. So this is sample space. So this A complement, this is A complement. Okay, so this blue shaded colors, this A complement. So this is the explanation based on Venn diagram. Alright, so this is a mathematical explanation. So the same example in example 3.3, so just example 3.3 mean just we consider 3 times tossing a coin. So if an event A is defined as one head in 3 tosses, such that A is equal to H, THG, or HTT, then the complement of A is a complement is equal. So the event space A complement should be equal to this one. So probability of A complement is equal to 1 minus probability of A. So we have probability of A treated as probability of the event. So probability of A is equal to 8 over 3. So probability of A complement is equal to 5 over 3. Okay. Alright, so next, union. The union of 2 events is the event which includes the events of the either of each event or both event. So let us consider A union B. This is the notation A union B. Be the union of the event A and B. So that means if we consider any element belongs to A union B, if and only if that element belongs to A or that element belongs to B. Okay, so in this case, this A union B, this that A union B. Okay, alright, so this is the simple example for A union B. So we define this A is exactly one hit, so this is event based, and another B event defined as hit in the third cross. So that event B space is equal to this. So A union B mean we have to write on all elements, this A and B. So that means A union B is equal to this event. Okay, so we can write probability of A. You know, our sample space contains total 8 elements. So probability of A is equal, here we have 3 elements in this event space A. So probability of A is equal 3 by 8, and probability of B is equal 4 by 8, and also probability of A union B is equal 6 over 8. Okay, alright, so next we are going to discuss intersection. The intersection of two events is the event which includes the element common on both the events. Let us consider A intersection B. So this is a notation A intersection B with the intersection of the events A and B. So this A intersection B, this is that event A, this is that event B. So in this case we denote this as this A as blue color and B event B as yellow color. So that intersection area is equal to this one. Okay, so and also alternative, we can say in the definition maybe intersection, suppose one of the event or one of the element A belongs to or X belongs to A intersection B, even only if that X belongs to A and X belongs to B. Okay, so there's an intersection. So let's see one simple example. So 3 times tossing a coin, if an event A defined is exactly one head in 3 toss, and event B defined head in the third toss. So this is the event space B, this is the event space A. So the intersection A and B, so actually the intersection means common element. So in this case, that common element TTH as common element. So this TTH, this element belongs to A and belongs to B. So that means A intersection B is equal to TTH. So we can write probability of A is equal to 3 by 8, probability of B is equal to 4 by 8, and also probability of A intersection B is equal to 1 over 8. Okay. Alright, so next, mutually exclusive or disjoint event. So events are known as mutually exclusive or disjoint event when there is no common element or element among the event. So specifically two events A and B are known to be mutually exclusive or disjoint if probability of A intersection B is equal to 0. So that means that A intersection B should be equal empty. Okay. So for example, in our previous example, probability of A intersection B is equal to 1 over 8. So actually this is not equal to 0. So that means this situation, this A and B are not mutually exclusive event. So suppose in exam times, if they ask any given some 2 events or 3 events, so just to verify that these 2 events are mutually exclusive or not. So that situation, first we have to calculate the probability of A intersection B, just to check whether that is equal to 0 or not. So suppose that is equal to 0, your answer just this is mutually exclusive, or otherwise not. Okay. Alright, so this that based on Venn diagram explanation. So this that event A, this that event B. So in this case, we don't have any common element for event A and event B. So disjoint event or mutually exclusive event. Alright, so next, addition rule. So that addition rule. So addition rule, the identity probability of A union B should be equal probability of A plus probability of B minus probability of A intersection B. So we can use this addition tool for any situation, any probability calculation case. That means union, probability of union of two events is equal probability of first event plus probability of second event minus probability of intersection of two events. So example, previous example, if we calculate the probability of A plus probability of B minus probability of A intersection B, that should be equal 6 over 8. So actually this is also equal probability of A union B. Alright, so suppose this event A and B are mutually exclusive or disjoint. So that situation probability of A intersection B is equal to 0. So probability of A intersection B is equal to 0 means these terms goes to 0. So that means probability of A union B is equal to probability of A plus probability of B. So there is a special situation. Suppose if they given this event A and B are mutually exclusive or disjoint event, we can write probability of A union B is equal to probability of A plus probability of B. Okay. All right. So this is one of the examples. So A defined is exactly one head. So this is the event space, and another event C defined two heads in three tosses. So maybe possible event space C is equal to HHHTH AHHT. The union of A and C. Suppose if we write down the event space A union C, this is the A union C. But in this case, we don't have any common element for A and C. So that means probability of A intersection B, C should be equal to 0. So that means A intersection B is equal to empty. So probability of A is equal to 3 by 8 and probability of C is equal to 3 by 8. So in this case, this is equals to 0. That means probability of intersection C is equal to 0. So probability of A union C is equal to probability of A plus probability of C. That should be equal to 6 over 8. Okay. All right. So next section, conditional probability. So that conditional probability, so that is very important. So maybe later we will discuss that Bayes law and total probability theorem. So those theorems are just modified from conditional probability, or maybe we can say this application of conditional probability. Alright, first we are going to discuss the definition of conditional probability. The concept conditional reduces or changes of the sample space, and probabilities are computed based on the reduced or changed sample space. So probability of B given A denotes the conditional probability of event B occurring given that event A has already occurred. So this is just notation. So here important, this not division notation, this is conditional probability notation. So that's we can treat that conditional probability that event B occurring given that event A has already occurred. So it can be found that by dividing the probability of event A and B both occurring by the probability of event A. So this is that formula. So we can use that formula for this conditional probability calculations. So probability of B given A should be equal probability of A intersection B divided by probability of A. So actually in this case this is the fraction form, so this denominator term should be equal a given condition probability given. Okay, and also we can write A intersection B also equal B intersection A. So maybe we can write this one. True. So this is a simple example in example 3.3. So that means 3 times tossing a coin. The conditional probability of head in the third toss given that one head in 3 tosses is 1 over 3. So because this under the condition that one head in 3 tosses, the reduced sample space A is equal. So there's the sample space, that reduced sample space, because in this case they given that one head in 3 toss. So that reduced sample space exactly one head in 3 toss. And also a question may be a conditional probability of head in the third toss. Head in the third toss means only possible for this one. So that means this conditional probability should be equal to 1 over 3. and one of the three equally likely simple event of having cat in the third case. Okay, maybe we can use that our formula. So we can write that event A, that event B. So we can calculate the probability of A intersection B. So A intersection B, in this case we have, this is the common element A and B. So that means A intersection B is equal, yes, only we have one element, so the probability 1 over 8, and probability of A is equal 3 over 8. So that probability is equal, conditional probability should be equal 1 over 3. So this is exactly the same for our previous B calculation. Okay, but most of the situation we use that formula, so that is an easy way. Okay, all right, so next, multiplication rule. So that multiplication rule, so this is just expanded from conditional probability law. So our conditional probability law said probability of B given A is equal probability of A intersection B divided by probability of A. Okay, so we can write that from that equation, probability of A intersection B is equal probability of B given A into probability of A, or otherwise also that is equal probability of A given B into probability of B. Okay, that's why, you know, probability of A intersection B also equal probability of B intersection A. Okay, so we can use this way too. So maybe some of the situation, this multiplication rule application is useful. Alright, so this simple example, these two cards are drawn from a standard deck of 52 playing cards without replacement. So without replacement in, suppose if you pick one card, so from the 52 cards, then second time you have to one card from 51 cards, okay, without replacement. So the deck consists of 13 clubs, 13 diamonds, 13 heads, and 13 spades. So what is the probability that both the heart are heads? So in this case, maybe we can apply that multiplication rule. So probability of A intersection B, suppose if we define that A is one of the event, indicate that first card is head, and B is another event, second card is head. So in this case, our question, what is the probability that both of hearts are head? So that means A intersection B. So that means probability of first selected heart and second also selected heart. So A intersection B. So just apply that multiplication rule. So we can write this one, probability of A. So that means first selected card head. So total we have 52 cards. So in 52 cards set, 13 heads. So this probability of A is equal to 13 divided by 52. And second multiply by probability B given A. So that means probability of second selected card head given that first selected head. So that means in this case this is without replacement. So after first event occurred, so second situation we have total 51 cards, and already we selected one head, so we have remaining 12 cards, 12 heads. So that's this probability 12 divided by 51. So that should be equal 1 over 17. Okay, so this is one of the example for multiplication rule application. This is the end of the example for application of conditional probability. So in this case, there are following from the 100 senators from 108th Congress of United States. So they're given here two political parties, Republican and Democrat, and also two gender type, this male and female. So in this case, they consider this 46 Republican male and 39 Democrat male, and Republican 5 female, and in Democrat 10 female. So if we randomly select one senator, what is the conditional probability of getting female given that Republican was selected? So in this case, this is the given condition. So total we have 100 senators. So suppose if we calculate the sum of this second column, so 51. So we have total 51 Republican and 49 Democrat. And similarly, we can calculate 15 female and uh, 85 male. So in this case, they given that Republican was selected, so we have total 51 Republican. So question conditional probability of getting female. So given that mean this Republican was selected, so that means in this case just only our reduced sample size contain 51 outcomes. So that means first maybe probability should be equal 5/51. Okay. Well, otherwise we can use that our basic formula. So we can write down that first recall that event A is first event and event B is nth event. So in this case, maybe we can define this. A is the selected senator is female, and B is the selected senator Republican. Okay, so then we can calculate that intersection probability of A intersection B and probability of, then we can use it. Okay, so this is another way. Alright, so part B, if we randomly select one senator, let A be the event that the selected senator is a female and B be the event that selected senator is Republican. So our question are the event A and B are mutually exclusive. So actually in this case, first we have to calculate that probability of A intersection B. So suppose that value is equal to 0, then we can say this event A and B are mutually exclusive or disjoint, or otherwise not. Okay, so actually in this case maybe we can calculate some values. So the probability of A intersection B is equal to some exists probability. So actually in this case is not mutually exclusive event. Alright. Right, so next, Bayes rule. So Bayes rule application, this is also very popular in probability calculation in industrial field. So let us consider that sample space S is divided into three mutually exclusive partitions S1, S2 and S3. So that means S1 intersection S2 empty and S2 intersection S3 empty, and also S1 intersection S3 also empty. And an event H has occurred. So that means H is one of the common event for event partition S1, S2, S3. Then we can write that probability of H is equal probability of H intersection S1, H intersection S2 plus H intersection S3. Okay. So probability of S1 given H can be written as probability of S1 given H is equal to, first I apply that conditional probability law. So probability of S1 intersection H divided by probability of H. So then we can write probability of H is equal to this one. Okay. So finally we can write probability of S1 given H is equal probability of H given S1 into probability of S1 divided by this one. Okay. So actually this is maybe, for example, you are one of the company manager. Okay. So you received shipment from three different suppliers, S1, S2, S3. Okay. So each supplier's product has some of the defective items. Okay. So in this case, maybe we can consider S1, S2, S3 are suppliers. This H is the common event, so that is defective. Okay. So we can calculate the probability of defective item is equal probability of H intersection S1. So that means H intersection S1 means first suppliers and defective, second supplier defective. Okay. So after mix this all segments, so suppose if you want to calculate, just randomly pick one item, one defective item. Okay. What's the probability that that item came from first supplier or second supplier? Okay. So usually these probabilities directly we don't know that this probability, but these probabilities are we can calculate. Okay, so maybe that's the situation. Maybe we can use that Bayes rule. Alright, so maybe later we will discuss some several examples here, so hopefully you can easily understand through the examples. Alright, so this is the Venn diagram for Bayes rule. So this partition S1, S2, S3 are three partition in sample space. So also mutually exclusive for disjoint event. So H is the common event. So this rule can be generalized for any finite number. So two or more partition. So an ultrasonography machine identify 50.17% of the baby's S boy. A baby's boy when ultrasonogram identify boy in 99.47% of the times. And a baby is a girl when ultrasonogram identify girl in 99.83% of the time. A baby born scales what is the probability that baby was predicted to be boy. So in this case we define S1 predicted boy, S2 predicted girl, and H common event born girl. Okay, so in this case the shape percentages are very important. So first, if you write down that in notation format, then maybe we can easily figure out this problem. So an ultrasonogram machine identify 50.17% of the babies as boy. In second sentence, a baby is boy when ultrasonogram machine identify boy is 99.47%. And third one, baby is a girl when ultrasonogram identify girl. Our question, baby born is girl, what's the probability that baby was predicted to be boy? Okay, so then first if you write down notation. So our question asking probability of S1 given H, and also the given probability of S1 is equal 0.5417, S2 is equal 1 minus 0.5417. So that means in this case only just we have just only two possibilities, this predicted boy or predicted girl. Okay, so and then also the given probability of H given S1, and probability of H given S1 is equal to 1 minus that one. That means born girl when predicted to be boy. But in this case they given 99.47% born boy when predicted to be boy. Okay, alright, so probability of H given S2 0.9983 born girl when predicted to be girl. This directly they given this probability, but in this case this probability they given 0.9947 is born girl when predicted to be boy. So then directly we can apply that Bayes rule, then we'll get that answer. Okay, so directly write on that formula, then substitute everything, then we'll get that answer. That is easy. Alright, so this is the another example. So three plants C1, C2 and C3 is produced respectively 10%, 50% and 40% of company output. Although plant C1 is small plant, it is manageably high quality. So that means was just only 1% the product are defective. So that means this conditional probability of defective given C1 should be equal to 0.01. Okay, so similarly C2 3% and C3 4%. Okay, so these are conditional probabilities. So all products are sent out central warehouse. One item is selected at random and observed to be defective. Then what's the conditional probability that it's come from plant C1? So in this case, suppose if we define that event D as defective, then we can write down probability of C1, probability of C2, probability of C3, and also we can write probability of D given C1, D given C2, D given C3. Okay, all right, so the answer may be 1/32. And also maybe you can try that question. Maybe if you want to that answers, or if you need any help, just comment through this below that video. I'll explain or I'll provide that whole answer for you. Okay, So in next, independence. So independence also, maybe some of the situation independence also useful. So there's two events A and B are independent if probability of B given A. So that means there is no relationship between occurring event A and occurring event B. So there is no relationship between the two events. So there is independent. So those are separate events. So probability B given A is equal to probability of B, or probability of A given B is equal to probability of A. Or otherwise, maybe we can write probability of A intersection B is equal probability of A into probability of B. So this is very useful and also very popular. So suppose two events A and B are independent, we can write probability of A intersection B is equal to multiplication of these two probabilities. Okay. So example, this on our earlier example, probability of B given A is equal 1 over 3 and probability of B is equal to 1 half. So actually this obviously this is not equal, so not independent. Okay, so that means not independent mean these events are dependent. Okay, all right, so this is the last section of this slides for presentation. So this counting, so counting principle. So in this section we are going to briefly discuss about that counting principle, and also finally we'll use that counting principle or counting technique for probability calculation. Okay, so maybe later we will discuss, maybe hopefully maybe next video we will discuss some distributions. So that's the distribution we will discuss. This one is the discrete type distribution, hypergeometric distribution. So hypergeometric distribution case we will use this counting principle is very popular. Okay, and also this is very interesting topic. All right, so first of all, what's that counting? Often the multiplication principle is used, such as one intend to travel from point U to point V via point W. For example, this is U, this is V, this is W. Okay, so one of the indicate here U to V. Okay, so we are point W, so that means U to W, W to V. Okay, so from point U to point W can be traveled in R different ways. So we have R different ways to travel U to W, and T different ways T to V. So then we can calculate the total number of possible ways for travel from U to V. That should be equal R into T different ways. Okay, so this is very popular for in your real life. So everyday application, this most of the time we use this multiplication rule. Okay, so there's simple examples. So we have three airports, so MSP and PBG and ORT. So there are 44 flights between MSP and ORT, and 2 flights between ORT and PBG. So then maybe total, he has total 88 different size travel from MSP to PBG. Okay, so this is the simple example for application of counting principle. All right, so next, factorial. So factorial, this is the factorial of number of product of all the whole numbers from the number down to 1. The factorial of 0 is defined to be 1. So this is factorial, mean usually we denote this as 5 factorial, mean this is the notation 5 factorial. So that means 5 into 4 into 3 into 2 into 1. Similarly, 10 factorial mean 10 into 9 into 8 into 7 into up to 1. Okay, so this is the factorial. So this reading in mathematically we can call that is 5 factorial. Okay, all right, so these are just several slides. I think maybe following maybe 4 or 5 slides we'll discuss some general question or general application of counting principles. So how many different license plates are there contain exactly 3 English letters? So license plates are there exactly 3 English letters. So that means This is the license plate. So 3 English letters. Okay, so maybe first possibility is for 26 possible way, and second 26, and similarly third one also 26 possible ways. So that means total number of possible ways 26 into 26 into 26, so that should be equal 17,576 different license plates. Okay, in a sequence of any 4 digits. So this is the end of the example. So there's fin in maybe possible 0 also, maybe initial point also 0 also possible. So first question maybe repetition allowed. So that means we have 9 possibilities for first one, and second 9 possibility, third one 9 possibility, fourth one 9 possibilities. So first answer may be 9 into 9 into 9 into 9. And repetition are not allowed. So that means first if you have 9 several ways, and second 8 several ways, and third one 7 several ways, and last one 6 several ways. Okay, so these are that simple egg. Alright, so this is the another example how many different 7 place license plates are possible. First 3 places are to be occupied by letters, and final 4 by numbers. So then you can write the correct answers. Then maybe if you need any help, for if you need these answers, then just comment through this video. I'll explain, or I'll provide whole answer for you. Okay. Okay, so actually I also given that answers here too. So first you can try that question. Okay, so then maybe if you have any trouble, please let me know. So in this case also, first one is repetition allowed, and second one repetition not allowed. So that situation, repetition not allowed case, this may be a different answer. Okay, this is another example for you. So how many ways are there? There are 5 people in this class to give Strat 154 course presentation. There are 30 students in this class, session 9. Okay. Alright, so how many different letters arrangement can be made from letters? So in this case, that's letter arrangement. So first of all, we have to make sure and identify that how many different letters, or maybe some of the situation is exactly each letters as different letters. Maybe some of the times, maybe some of the letters gets 2 times so repeated, or 3 times repeated. Okay, so in this case, this first example, this fluke, so this word contains 5 letters, so each letters are different. F one time, L one time, U one time, K one time. So this total number of possible ways 5 factorial. Okay, and second example, propose. So in this case, it is P 2 times, O 2 times, R 1 time, S 1 times, E 1 times. So that means in this case, actually this total number of possible ways total we have 7 letters. So 7 factorial divided by 2 factorial into 2 factorial. Okay, because it's P 2 times, O 2 times. And third one, Mississippi. So in this case, total we have 11 letters, but S 4 times, I 4 times, and P 2 times. So 11 factorial divided by 4 factorial into 4 factorial into 2 factorial. Okay, and fourth one, arrange. So 7 factorial, we have total 7 letters, so 7 factorial divided by 2 factorial into 2 factorial. Alright, so next, permutation. The number of ways in which subset of object can be selected from given set of objects, where order is important. So in this case, this order is very important. So for example, given a set of 3 letters, this A and B, A, B, C. So how many possibilities that there are selecting any 2 letters? So where is order is important. So we can write this 6 possible ways. Okay. This general form, these are different items. without repetition from n different items can be arranged in n into n minus 1 up to n minus r plus 1 different ways. So this way of counting is all known as permuting or permutation, or arranging that means r different items from n different items. So this number of arrangement. So npr, n factorial divided by n minus r factorial. Okay, so that is permutation. This r number of item or different items arranged from n different number of items. Okay, and also this, you know, that n factorial mean n into n minus 1, n minus 2 up to 3 into 2 into 1, and also 0 factorial should be equal to 1. Okay, so this simple example, two different items could be arranged from four different items. So maybe possible answers is 4p2 or 4 into 3 12, or otherwise you can use the permutation formula for p2. Okay, so five different items can be arranged among themselves in 5 into 4 into 3 into 2 into 1, or 5p5. Okay, so this is a simple example for the permutation combination. So this is very important, this combination, the number of ways in which subset of object can be selected from given set of objects where order is not important. So in this case, the probability calculation case, this combination is very useful, because this is just, for example, we have 30 students in this class. So how many possible ways for selecting 5 students from the 30 students group? So that situation we can use that combination formula. Okay, so given simple examples, given that set of 3 letters, this a comma b comma c, how many possibilities are there for selecting any 2 letters where order is not important? So AB or AC or EC. In this case, your selection, not order, is important. Okay, so this general form are different items without repetition from n different items can be selected NCR. So that means we define that NCR n factorial divided by n minus r factorial into r factorial. Okay, so NCR is obtained, actually this NCR obtained by NPR by r factorial. So meaning the number of is lowered by factor of r factorial. The number of ways r different items could be arranged among themselves. Okay, a simple example, you need 2 people on your committee and you have total 5 to choose from. So you can see that it's the without repetition, because you can only choose the person once. The order doesn't matter. You need 2 committee members, but it doesn't matter who's chosen first. So how many combinations are there? So in this case, this first we are finding this indicate that each peoples are different colors. So we have total 5 people. So you need to select 2 people from this 5 people group. So the possible ways, so total 10 possible ways. So suppose if you apply that, this is first, this is that graphical way. Okay, so suppose if you apply that combination probability 5C2, total we have 5 people, you are going to select 2 people from 5 people, so 5C2, so that is equal to 10. Okay, all right. So and the example, 2 different items could be selected from 4 different items. So that answers maybe 4C2, or maybe you can use that our basic uh, combination definition. Okay, so 6 different ways, and 5 different items can be selected from 5 different items, so that means 5C5, that should be equal to 1. Okay, all right. So and also in this combination case, this NCR always equal NCN minus R. Okay, so maybe we can verify that answers based on simple example 5C2 also equal 5C3. Similarly, 10C7 also equal 10C3. Okay, so maybe some of the situation this is useful for directly you can use that this application. Okay, so this is the end of the example. Two men and two women from firm will attend a conference if the firm has 10 men and 9 women. So that firm has 10 men and 9 women. So 2 men and 2 women from firm will attend the conference. So we have to select 2 men from 10 men group and 2 women from 9 women group. Okay, so how many different ways can select conference attendees? So stage 1, first select the 2 women from 9 available women group. So that means 9C2, so that's equal to 36 possible ways. Similarly, 2 men from 10 men group, so 10C2 possible 45. Then apply that multiplication rule. 36 into 45 should be equal 1006 to all. So 1620 number of different ways for selecting 2 men and 2 women from 10 men and 9 women group. Okay, there's another example. A basketball team consists of 2 centers, 5 forward and 4 guard. In how many ways can coach select starting line up to 1 center, 2 forward and 2 guard? So in this case also we can apply that multiplication rule and combination. So 2C1 into 5C2 into 4C2, so total 120 ways. Okay, all right, so this is that identification, permutation and combination. So both are number of ways selecting R items out of n items, so repetition are not allowed. And permutation case order is important, but combination case order is not important, just selection. Okay, and permutation mean arrangement of n items taken R at a time, and combination means subset of n items taken R at a time. Okay, and so npr n factorial divided by n minus r factorial, and ncr n factorial divided by r factorial into n minus r factorial. And also clue words, arrangement, schedule or order, and combination case clue word, group, sample or selection. Okay, so this that is the identification for your these problems. And also maybe you can use in your calculator GI 83 or 84 calculators. You can use that permutation for this option NPR and NCR. Okay, so that means NPR means 5, just choose that NPR and 3, so 5P3. And similarly combination, so 10CR means use this NCR. Okay, so NTI 83 or 84 or 84 plus calculators has this option. Maybe different calculators has different options. So suppose if you need any help for that calculator calculation, let me know. I will explain. Alright, so this is the one of the example for probability calculation. A group of 11 seniors, 5 juniors, and 4 sophomores have volunteered to be peer tutors. Mr. Lucky needs to choose 12 students out of the group. How many ways can the 12 students be chosen? So that means in this case total we have 16 students. So without any restriction, so how many possible ways that selected 12 students? So 16C12. Okay. And second, if the students are chosen randomly, what's the probability that 4 seniors, exactly 4 seniors, exactly 4 juniors, and exactly 4 sophomores? So this probability case, the denominator term 16C12 and numerator term 7C4 into 5C4 into 4C4. Okay. And third one, if the student are chosen randomly, what is the probability that 4 seniors and juniors and at least 3 sum of years. So in this case this is fixed, but these are not fixed. At least 3 sum of years mean at least 3, minimum 3, maybe 3 or 4 of, yeah, maximum we have 4. Okay, so suppose if you consider 4 sum of years, juniors also 4. Okay, and suppose if you consider 3 sum of years, this juniors 5. Okay, so in this case the denominator term exactly same for previous one, 16C12, and numerator term just you have to calculate first 7C4 into 5C5 into 4C3 plus 7C4 5C4 4C4. Okay, so that's the probabilities. So I also given that final answers here. Okay, so you can write, then maybe if you need any help just comment below this video. Okay. Alright, so this is the end of the example. Say a box contains 24 ancestors, 4 of which are defective if 4 are solved at random. Find the following probabilities. Exactly 2 are defective, all are defective, or none is defective, so at least one defective. So this is that your practice, so you can write. Okay, so then maybe if you need any help, then I can explain. So this is the example. So actually in this case there's not application of counting principle. So actually this example for application of independence probability. Okay, try it yourself. Okay, I also given these answers to here, so you can try it. So this is the ending position of this presentation. So please don't forget to subscribe my channel. Thanks for watching my video. So in future also, maybe hopefully maybe in our next video we'll briefly discuss about some discrete type distribution, and also continuously I will explain this every statistic section. So especially maybe later we will discuss some mathematical calculation, this everything step by step. Okay, so see you on next video. So please don't forget to subscribe my channel. Thanks for everyone. Thank you.